Alright, so in this lesson we're going to start looking at the equations that deal with lenses and another way that we can mathematically predict the types of images, locations, and heights of images created by a lens. So we have two equations with lenses that help us predict image height, image location, object height, object location with a lens and magnification for a lens. And it's worth pointing out those two equations, what I call the thin lens equation and the magnification equation, look exactly the same as the magnification equation and the mirror equation for mirrors. And in fact, mathematically they're very, very similar. The only difference between these two equations, the mirror and the lens equations, is there are a few sign conventions that are a little bit different, like where is an image located compared to an object if it's a real or virtual image, and which mirror lens is a converging lens versus a diverging lens, or a converging mirror versus a diverging mirror. So we look at kind of a quick chart for sign conventions for lenses. Some of these things are the same as they are for mirrors, but they have a slightly different interpretation for lenses. So if we look at image distance, real images have positive image distances, virtual images have negative image distances. This is exactly the same as it is for a mirror. The only difference is a real image for a lens is on the opposite side of the lens, a virtual image is on the same side of the lens. This is the exact opposite of a mirror, where a real image for a mirror is on the same side of the mirror as the object is, and a virtual image is behind the mirror. Image height being positive is upright, negative is inverted. That's the same as a mirror. Focal length, positive is converging, negative is diverging. The only difference is that the converging lens is a convex lens, where the converging mirror was a concave mirror. The diverging lens is the concave lens. The diverging mirror was the convex mirror. So that's flipped around. Convex and concave is flipped. And of course we could have positive image distance, which would be a real image, or a positive object distance, which would be a real object. And we could have a virtual object. And I put a little asterisk here for virtual objects because sometimes it's useful to define an object as a virtual object if you have a system of multiple lenses, where that would come into play as if you had a lens and a system of two lenses that are separated, let's say, by 5 centimeters, and the image formed by the first lens is 5 centimeters behind the image behind the second lens. It might be useful to call that DO negative 5 centimeters for the second lens to actually begin to predict what the final image location is going to look like. So let's do a quick practice problem. And so we have a 1.7 meter tall person standing 2.5 meters in front of a digital camera, and the camera is using a converging lens with a focal length of, well, 5 centimeters or 0.05 meters. And we want to determine whether the image produced in this situation is real, virtual, upright, or inverted, and enlarged or diminished. I guess same size is a third possibility here. So real or virtual. So the way to figure this out is to find where is the object at, or the image actually located. So 1 over DO plus 1 over DI equals 1 over F. So if we solve this out, 1 over DI equals 1 over F minus 1 over DO. And so if I work that out, 1 over DI is equal to 1 over 0.05 minus 1 over 2.5, which actually equals 19.6, yep. And so if you take 1 over 19.6, you get 0.051 meters. So this is a real image. It is located with a positive image distance. It's actually going to be located behind the lens. If you think about this, a digital camera, the object is outside of the camera. The image produced has to be inside of the camera, behind the lens, in order for that image to be collected by the camera. So upright or inverted, enlarged or diminished. Both of these we're going to use the magnification equation. HI over HO equals negative DI over DO. And so if we calculate the magnification, negative DI over DO, we get negative 0.0204. And what I can say is that it's diminished. And I can actually figure out what the object height is. That is 0.037, or negative 0.0347 meters, so it's also inverted. So there we were able to figure that out using both the lens equation and the magnification equation. Now, a mathematical aside, and you've already heard this once before, there's a common mathematical mistake or a common algebra mistake to watch out for. And here's the common mistake. 1 over DO plus 1 over DI equals 1 over F does not mean DO plus DI equals F. Doesn't matter how many times I say that, there's going to be somebody who tries to do it this way. So if you actually try to figure out what f is in this equation, you have to find a common denominator, add the two fractions together, and then invert those two fractions. So you notice f is not do plus di, it's actually do times di over the sum of di plus do. Now, this is an easy mistake to make, so be very careful with the algebra with these problems. It's also worth pointing out that we could arrange the equation for do or di in a similar fashion. Find a common denominator, add the fractions together, invert the fractions, and this is what you end up with for both of those. It's worth pointing out that these three equations look exactly the same as the three for the mirror that we talked about when we had the mirror equation lesson. So one thing to point out about lenses is the mathematics with lenses and mirrors are very similar. The types of problems you deal with are very similar, just you need to keep in your mind some of the sign conventions that are a little bit different.